Again, I'm Chip-Ping Lee and the Program Manager of the Energy Conversion and Combustion Sciences. I'm 5 months old at AFOSR. I thought I was youngest, but someone beat me and on Monday. I took over this portfolio, which has been built very successful, managed by very respected program manager, Dr. Julian Tishkov. And I was expected by my bosses here, also more by myself, to make this portfolio even better. That makes things quite difficult. That's why I'm trying to do. Only way I figured out is I do it as completely revamp the portfolio, take it apart, and rebuild it. And I will tell you the story today. And I will tell you basically the previous portfolio really did a great job in the area. It is because the effort funded by Dr. Tishkov, I'm able to do a lot of things that I like to do in the new portfolio. And also, it is because those work pointed out the necessity to revamp the portfolio, also pointed out which direction I might do it. So it's all built on my great colleague, Dr. Tishkov's achievement. And here's where is he? So again, and the brief description of the portfolio. What does it do? It tries to understand the combustion fundamentals in the way we never did before, in the region which we're interested at. And we want to quantify the rate controlling process on scales. Why I want to do that? Because if we quantify the rate controlling processes, we know the scales, we can manipulate those to have the phenomenon behave the way we like. And the scope, well, we are interested in all the multi-physics, multi-scale phenomena in the combustion process and relevant to Air Force propulsion applications. And then, and all those, I apologize for that. And all the aspects of the above described and the phenomena are interested, but we do have the emphasized sub-areas. And those are combustion diagnostics, turbulence combustion experiments, and combustion modeling and theory, and innovative chemical to mechanical energy conversion for propulsion applications. And the way we structured it actually follows our way to do research. We need our tools, we need our sensory equipments, we need to be able to see things. That's our diagnostics. Then we need to watch the nature to see what it is and to see what happens. That's the experiment. Then we need to learn that. We need to develop a theory, summarize our understanding in the theory, building our tools to predict that. Then we can go around to explore even a little bit more. So that's the more philosophical approach. But here is more the attributes of the portfolio as we go far more fundamental into turbulence flame structures, turbulence flame speed, the other properties. In the modeling area, we'll go far more first principle based as we want. If we cannot do the first principle, we'll based on our model on experiment data rather than some, uncorrelated assumptions. We will focus on Air Force relevant conditions, and that does not mean I try to focus to each propulsion engine type to make it apply. That's happen to be where the most interesting phenomenon happens, where we will understand things. And the sub-area, as I talked about, diagnostics, and we do experiments. We try to focus on the region at high compressible, high Reynolds number conditions, which happen to be relevant to Air Force system, which happen to be understudied before. I will have a chart to show you on that. And the next one, And in the modeling and the theory, we'll focus on the first principle-based model and the experiment data-based turbulence model. And we'll focus on the numerical experiment. We'll use numerical experiments as a tool, allow us to explore the nature, explore and phenomena. So that's why we try to use it. And the portfolio already have an element to use it. We'll probably expand that. We found out that's a successful way to supplement the physical experiment. And the last, we'll explore different type of the combustion regime in the area we haven't explored before. And we'll also, in the case, if we have too many rate controlling processes, we can really make sense or handling it. We can injecting and imposing a rate controlling process to make the phenomenon to behave the way we like. So those line of the exploration we're going to take. Then let's go into see the next page. What is the key combustion phenomenon? I'm relatively fortunate because in this area, there is a key phenomenon has been recognized for hundreds of years, which is called turbulence combustion or turbulence flame. But in the area we're interested at is really underexplored. So that's the focus. So turbulence combustion, which is a key combustion phenomenon in most of Air Force propulsion systems. The next statement. It is most important determining factor for the operability and performance. Next one is least understood area in the basic combustion research with rather large uncertainties, which prevent us to predict it and properly. The next one, which happened to be confluence of this grand old fundamental scientific problem, also have immediate impact, long-term and short-term. The basic data we're getting and will allow us to understand the flame structure, flame property, and also some of things can be even directly used for the design of next generation engine. It's a perfect confluence. And the next one is the recent advance, as I mentioned, in diagnostics from the persistent investment by Dr. Tishkov provided the needed experiment tools. And that's just a further substantiation. That's some typical engine. I think that's the only chart I took from my predecessor's charts. And all those three engines, they all have some kind of combustor. They all have some flame. And those flame structures, the way they propagate, determines how well they perform, how big the combustor is, how heavy it is, all those things. And do we understand them? That's the problem. Well, that you will see, draw your own conclusions. Typical people understood this called the first one, called the Laminar Flame. And it's nice looking propagating flame. And well studied, many publications, people use it and to do things to understand. But in our engine, we have a flame like this because that flame propagates too slow. And have those really curved shape. We don't know what the shape is. And very few experiments has been done. And in those high Reynolds number conditions, if we push Reynolds number even higher, what do we see? This is the flame we see. And so that's the critical phenomenon we're going to attack. And how do we do it? We have to understand, what sort of conditions, where we're going to do the experiment. This is what we call the regime diagram or regime map. Basically have all the critical scales they want. It can be drawn in many ways. You can have Mach number here. You have one axis represents the chemical reaction, which usually we call Dunkel number. It's a ratio of the chemical reaction time versus the resonance time of the fluids. And we have this one. We can say there's a Reynolds number, some kind of equivalent Reynolds number. You can draw it in many ways to basically tell you tell you the impact of the different critical scales. Then this is a little very pretty diffusion flames. People have been studying this into that for many, many years. Some of the PIs still study it in the previous portfolio, and they try to evaluate different chemistry process for different fuels. And where do they sit? They sit right here. Okay, let's see, next one. This is a little flame ball generated from bomb. And that's typically equivalent to the condition of the auto engine. The mixture, how it's burned in the piston, even a little bit slower than that. Where do they sit? They sit here. Next one gets prettier. This one you have seen. This is the flame at high readiness number, high Mach number conditions on its way to detonation. I have a movie later showing this. Where do they sit? They sit right here. Okay? This is the auto engine. It's our engines. Where do our engines sit? Somewhere right here. Do we know? We don't know. But we know it's somewhere in between. It's very turbulent. It's somewhat compressible, depends on type of engine. If you have a jet engine, it's Mach 0.1. If you have other engines, become higher and higher Mach number. You have PDEs. Here you go. And I have been talking to TDs, different engine companies, and do you guys know these conditions? Oh, we have U prime bar, which is the standard, the standard deviation average. I said, that's not enough. Do you know the spectrum? We don't know. And we have some gases. I said, no, we're doing science. We need something better than gases. So we don't know where they are, but we know it's from here to here. That's the previous work supported in the previous portfolio already tell us, since we're here, we need to understand somewhere here, and step by step. So that's really the contribution of the previous thing, and tell us where to go. There's a future things, like a detonation-based engine. They appear. So what's the questions? What's the observation? Where little data available in this region? I got lucky. So I have some places I can work on in high range number, high compressible conditions. Key questions. What do we want to know? The flame properties, flame structures, regime boundaries. Where does the flame change its shape, change its characteristics? Critical scales. How important are those scales? Any other scales we need to use to control the flame? What's the rate controlling process? Chemistry and heat transfer, all those things. And we need to know those things. So what's the moral of what's the takeaway message? Well, we have very little data now, and we need better definition of the conditions. We need to go back to understand those things. And I have my reasoning why that was being done, why so many work was done, and in those low readiness number regime. I wouldn't further speculate on that. So this is the one of the experiment I call lower bounding case, and shows produced at the flame ball. And there's a further information, further message to be delivered. What happens? They have inner chamber. They generate those turbulence through those fans, through those motors. And those are the flame ball shape. Those are the location of the flame ball, the average location with the time. So this flame ball just grows. And the slope of this curve is the turbulence flame speed. It's the flame speed. You can see at this modest Reynolds number, the speed is already increased. Not only for each Reynolds number at the beginning of one speed, it's increased through the course. So this is the effect of turbulence. And it's already showing the fact, which is usually not really well considered from basic scientific understanding all the way to the design tools. So what does tell us? Turbulence already affects flame structure and speed at relatively low Reynolds number condition. Upper bounding case. This is when I was also existing PIs, and it's when our Navy partners, they had a great team, and when our NRLST, supplemented by one of her younger researchers and from Ukraine, and they explored not only and for this type of the detonation flow, also all the way to the supernova explosions, all those things, and they basically applied similar numerical simulation as exploratory tools to do experiment, explore all those things. So really great things come from that team. What we see here, this is the sort of flame surface plot. You see how perfectly evolved. You see those brushes. It's a little tiny things, which is like night and day difference. What do you see from that little blue flame? You know, those blue flames really pretty. Do you see that? No. What are these? Those are pressure. You see what happens as the flame surface keep growing. You have more and more energy release. Finally, you don't have enough relief. The pressure accumulates. Then you have a sort of shock front. Where does that lead? That's lead DDT. And then you can see this is how flame evolves. It's going, and you get more and more little structures. And then it's become really chaotic. Finally, the order arises from it. Water arises from it when you see a little surface going to the right, become detonation. Then detonation is a very defined structure in the combustion. And so what happens is, at this very high Reynolds condition, the turbulence significantly increases the flame surface at the global burning speed. If the condition on the right-hand side, I haven't shown you yet, satisfy, the DDT start. This is another great thing came from this group. And this is once people write this down, start explaining it, it's super simple. It's obvious almost. Why didn't I figure it out? Because I hacked on this problem for 20 years. I never saw this. What it says, this is sound speed. This is the ratio of density before and after flame. This is turbulence speed. If turbulence speed is greater than this criteria, it goes to DDT. What happens is, and because you rely on sound wave to relieve the energy produced from those reactions from flame. If the energy is not able to release, if this thing goes too fast, and then pressure accumulates, then you're on the way to detonation. And so they came up with this. They got, I think they got some nature, some paper in the, you see I'm in the combustion business. We don't usually publish the paper in the Nature or those things. We have our own journals. This is our advantage. Probably one of my PIs won't get Nobel Prize. But they start publishing those things, being appreciated. So this is one of the really interesting things, really make myself kick, because I was doing the similar things. And why did I thought about this, think about this? Okay, so, and I go into next chart fairly quickly. I want to get more physics. And the next two chart basically says, we're dealing with multi-physics, multi-scale, and the phenomenon. The turbulence combustion is quintessentially multi-physics, multi-scale. And next thing I want to say is, and it's intersection of two highly nonlinear process. If you think John Schmischer's and Doug Smith's life stuff, he has one and nonlinear and process. I got another one, chemical reaction terms. They're exponentially dependent. And so make my life miserable, I can say. But I'm optimist. What I see is you have things can become orderly, detonation or something. So in all those chaotic things, something may happen after we study this. We may learn something new. And the second one, you have all the energy interactions, diffusion and radiation, all those things. And we have, if we want to consider real engine, we may have droplets. We may have two-phase combustions, all those things. And we have all numerical issues we have to deal with. So what do? We have to do multidisciplinary collaboration is essential to the success in this area. Next one. Well, you see, the portfolio to have some underpinning philosophy. Each program manager has their own way to do it. It's not the only way, but it's one way. As long as it makes sense, we do it. So here, what we like to do is basically we try to understand the nature, building our observation tools, get our understanding from experiment or numerical experiment. Then we understand the key physics. We try to quantify the rate controlling process. If we can, and we can establish a theory, which we can use to predict the future. And so it goes back. If we cannot, then we are not totally out of luck. We may be imposed on other processes like plasma, catalytic, or those things to create a little rate controlling process. Then we can manipulate the phenomenon the way we like. And if we understand that, we can do the step. So that's sort of a philosophy we're following at this stage. In next year, maybe 3 years, 4 years, and depends on what we learn. And there's a collaboration with other agencies. And to save some time, I will stress only 3 points. One is we already have a pretty strong collaboration. The number 2 is we divide the problem. We divide conquer. For example, this portfolio, and since now we will focus on the highly compressible, high Reynolds number conditions, more relevant to Air Force engines. I will leave and laminar flames and low Reynolds number flames more to the auto engines, ground systems, to DOE and NSF. NSF support everything, and to DOE to handle. So that's, and we already have the talk with the key DOE personnel, my counterpart, and people in the Sandia. Sandia have a whole bunch of really excellent experts, and their work is cool. So if they can focus on this lower and the Reynolds number regime, push up, that will help us and will help them. We'll work on this area. Has not much work been done before. And I will go, and all the talk, we met at different meetings, but I'm going there in a couple of weeks to further solidify this relationship. And then, so we divide the problem. That's basically, and different agency does different things. As John mentioned, there's a little unfortunate things about NASA's effort on hypersonic. I will not further drill on that. And the last one is the macro. We do have multi-agency called the Coordinated Committee of Combustion Research, created, actually largely created by my predecessor, Julian Tishkov, many, many years ago. Actually, I assumed the leadership of that. That's working effectively, help us. The positive role will continue. So the bottom line is multi-agency collaboration benefits everyone. That's how we do it. Now we go to my first area. This area is a very strong area under my predecessor portfolio. I will leave as it is. And basically, and we will use that to understand the key phenomena, quantify the rate controlling process. We have 3 world-leading experts, 2 of AFOSR stars, Ken Carter and Jim Gord. Then we have Ron Hansen, and who is the member of National Economy, and all 2 PKs, 2 PKs awardees, and in the portfolio. So you cannot get better than that. And this area will be continually supported. And not only for supporting my current effort, also to create opportunity for the future, because those investments has to be made earlier. You know, a lot of them start with Rick Perry type of portfolio. Then I'm sort of end user. They provide the lasers and maybe spectroscopies. I take over the spectroscopies of end use. So, and the focus are the signal generation and related spectroscopy. The other one is I will push a little bit more to the 3-dimensional and volumetric scanning image. That's really crucial for our turbulence research. And then the other thing is, after we got those 3-dimensional data, what to do with it? We need some numerical tools to do it. Oh, I missed one. And we're starting looking for the multi-phase diagnostics to quantify the size of spray or those things. So support current needs and prepare for the future. So that's what we do with the diagnostic. I'm going to show you some example. What? Okay. This is one of the really great work done by the lab. It's really highlight of this, the lab task. It's kilohertz imaging. The principal investigator is Ken Carter. This is what he did. And actually he did this in Germany and collaborate with his German partners. And this is a little flame, which is propane and diluted by argon. They dilute it to control the where start ignition. And this is they call lifted flame. You have no flame until you reach here. And this is the box, and which the diagnostic thing is is being focused at. And this is the size of the box. And you see the red and the green are different color, represent different velocity vector, different altitude. The white is OH Pliff, which actually happen to be one of the intermediate species in the flame zone. Then this is the movie it plays. And the reason I like it to play is not for the prettiness. It's pretty. It's like Christmas tree, and it's very refreshing. But I really want to indicate here, you see the flame goes. Sometimes the flame just go away. Then new flame appears. You see that new flame appears. Those kind of events sometimes happen 5 times a second, or maybe 25 times a second. Sometimes doesn't happen every 5 seconds. So it's very difficult for current people using the statistical approach to represent where's the statistical likely location where things happen. What's the times like to happen? All the run simulations, you take bars on the Navier-Stokes equation, you take an average, you get higher moment term. Probably we have to rethink how we model this. That's kind of phenomenon really is the driver for the thinking. We have to get those data first, allow us to understand the phenomenon before we really start developing models. Because this is kind of things. If statistically you take an average, what's the average location of the flame? Where it starts? Doesn't tell you. Couldn't do it. But anyway, go back to the thing. So this kind of diagnostics is what allow us to go to the next step. And the next one is the one by Jim Gord, and is co-funded with Perry with similar fashion. He handled the physics. I've handled a little bit of spectrum and use. But I really not happy with him because Jim Gord sent us 3 pictures. He took 2 of the better ones. But I think this one has more physics, whatever. And what happened is this one, they use 2-photon process. I might well just get everything in there. I'm going to play the 2-photon process from bottom to the N3 state. Then, let the fluorescence go from N3 to N2. One of the big problem in this kind of process is you have those, if you're shining too much laser in the too long of time, and you have single oxygen generated from those water and other species, then which will contaminate the signal. And if you have a femtosecond laser, you see if you jack up a power, it's this shape. If you have a picosecond laser, it's getting better. What happens if you narrow the laser and you don't have much of those additional and hydrogen? Basically, when you do your diagnostics, you introduce some additional hydrogens. So the picoseconds all converge. So you see the usefulness of a picosecond. Rick actually showed 2 other things too. But still, I'm not happy with he take the better looking pictures. But anyway, so go on. That's life. And so basically, that's a 2-photon process from femtosecond laser. And then we look for the future now. What do we do with the X-ray? And what we do with multi-phase. This is another great collaboration with DOE. At the Argonne National Lab, they have those X-ray sources. And basically, they produce those X-ray sources, and they're shining through water jet. Basically, what we do is also the PIs are Ken Carter and his co-PI, Steve Lin, which happened to be the one of the still living. He's not that old, and in the two-phase flow, because there's a one well-respected and droplet two-phase flow expert, and Jerry Faith, and who passed away maybe 8 years ago. We are still waiting for the new rising star in this area. So we do two things: the phase contrast imaging to get you the look of the flow, and the radiography basically is absorption measurement. So as you see the shape of those droplets. Here you see the absorption line when you move along, and you see the different absorption peaks. And this line of work will be further extended, and there's extended under the portfolio, under the lab work, and particle sizing experiment, and use the same X-ray source for the supercritical and injection flows. So those so much for the diagnostics. That's what has been done. So what will portfolio do in the future? That goes to the next sub-area. Next sub-area is high Reynolds number, high Mach number turbulence flame experiment at the relevant condition range. And in the last 6 months, we have been scrambling, but we have very good support from government proposal review team. And those efforts will focus on the flame propagation, the flammability limit, and the flame combustion stability. In other words, the basic flame properties. And we started with single phase. Eventually, we moved to multi-phase, and then which is made possible by the diagnostics. The key requirement of those experiments, as laid out in the BAA, is we can understand the basics, quantify the rate controlling process, also provide the data for developing and validating the basic model assumptions. I put model assumptions instead of model. Specifically means we need to understand basic physics and before we build models. So we need to drill down the model assumptions. In any of those experiments, it's one essential thing. We have to know the turbulence property. Otherwise, we don't know and the flow conditions. Then how do we study that? And the proposal has been considered, funded by. There's one proposal dealing with the critical scales and relevant conditions and inherent instabilities. And there are 4 proposals in the experiment. So we are relatively fortunate. We received some very high quality proposals. We select 4 of them. So I will pick 2 examples to discuss. So those are the flow configurations. This one is more like engine configurations. This one is high speed. The young PI, courageously, he invested all his startup money, Stanford graduate. And I warned him, I said, this thing may not pan out. You may not hand your tenure on this. He said, I'm going to do it. So, and a very good proposal. We're working with the lab. And the other one is from Georgia Tech. I will discuss a little bit. And the other one is try to take the traditional approach to see it works. And we'll keep supporting this work, pushing higher in Reynolds number. So why do I do this? The understanding starts from observational data. We want to know what flame look like at those conditions. And University of Michigan experiment that's been funded actually went out, right? And and this basically 2 flame sources, and let flame propagate in the middle to see flame shape. They have done this at relatively low Reynolds number. This is the field imaging. They see that's the flame front. That's what a flame front look like. So they're going to explore in this regime, which get close to the jet engine type of things. And then they're going to look in how this kind of interaction, which when eddy going through and eddy going through the flame front, and then the vertices become suppressed after going through the flame. So this kind of interaction. And they are also going to look at the local extinction. And this is the CH pliff, or sometime flame is gone here, then we'll reignite. That's further basically tell us the the point that we need different rethinking about our current mindset of those turbulence flame. Can we get some statistical description of that? May not be. We have to do, okay. And then I'm going to, since I'm running out of time, I'm going to quickly going through this and discuss two more charts. And then the second experiment is the one, and Georgia Tech is undertaking. They basically have this slug of flow, and they ignite the flame. For middle of flow, watch the flame ball to grow. They're going to watch in this region. They're going to look at those properties. So those kind of great experiments online, and we expect to get those results in 2 or 3 years. So next one is the combustion theory and the modeling. There, we're going to focus on more first principle combustion modeling and more physics-based and turbulence combustion modeling. And if we cannot do first principle, as I said, we'll rely on experiment data. And we'll rely on much less on the ad hoc assumptions. The numeric experiment will focus, and then we'll find a way to do the data fusion. We'll try to apply the DDDAS type of the approach and do a combined numerical experiment and experiments. So I will go to the next page, which I will highlight some of my the ab initio chemistry, combustion chemistry modeling. We have been used to what they call this Arrhenius model. The Arrhenius model is good, served us well, but it has its limit. Basically, when the most of the population below so-called activation energy, below the bound breaking energy, and the model is good. When, and most of the things and above that energy, the model breaks down. We don't know the chemical reaction rate. And when we are in the thermally, non-thermally equilibrium, we even have a trouble to define temperature because at each state you can define different temperature. So what we do, we have to look at, sum up all the states and start from first principle and build the new models. So that's one of new focus, and which is a new exploratory area considered by this portfolio. Next one. And if we have a fairly complex reaction like this, and the reactions, this is benzene, goes to different stages. You have a lot of intermediate species. Which way reaction go? In your kinetics, how do you pick most important one? That's the challenge we decide to take on. There are two aspects of it. You can use this approach, use the first principle, like work with Mike or those people, calculate the reaction rate constant. That has already been done, but supported by DOE and us. Probably I will keep this area flat. But the new area we like to go into is, now you have heard this, okay, you have heard this 3,000 step reactions. What do we do with it? We cannot do much about it if we have start that big. We do sensitivity study to reduce it. There's another way, which may not pan out, but we're willing to explore. We started with first principle. We started with the energy surface. We see what's most likely and approach to craft those reaction steps. And so this is a new explore area. So that's where I say the things will be far more ab initio than it was before. And then I will skip this last movie since I got only 2 minutes. And this is where the fun thing will happen after we understand the basics. Understand the basics is fun. Once we understand it, we're really happy. But that's where we're going to explore the detonation, and we'll explore the combustion regime we have never explored before. The detonation we touched upon, we're going to take a look at more distributed flame, where flame peak disappear. That's all kind of advantage for that. And the NOx going down, the engine heat load going down, the engine heat signature going down. So we're going to explore that. And plasma and catalytic assist combustion. Maybe we take some of nanoparticles, plasmonic, and type of the things allow us to help us for the ignition, all those kind of things. Then we look some fun thing are direct conversion from chemical energy to mechanical energy, and then we look for different type of fuels. So those are the third area. There's an example for that. I think I'm going to skip that and go into the summary and looking forward. The advanced diagnostics will keep investing, and the turbulence combustion and experiment effort. And we do step by step with gas phase, eventually move to the multi-phase. Within 2 years, those data online. I think with 4 or 5 years, we'll have the data for the liquid phase. And that will take care of it for a while because we had a great leap in the diagnostic last 20 years. We'll take advantage of that. And on the meantime, we're funding a relatively modest effort, taking the more updated and the diagnostics. So this is this effort. The next effort is the modeling. We'll focus on the more first principle based models. And actually, we're taking fairly large risk and to explore. And the last one is innovative energy combustion process, as I mentioned, and explore and those new game-changing ideas. So there are some technology transfer from this portfolio. It's really enormous. I just list some and quick ones. There's diagnostics. There's a JetSurf, came from USC. It's a reaction kinetics. Here's my closing statement. And any questions? Oh, I guess that's for you to ask.
We have time for one quick question.
So how do we measure success here? I mean, are we trying to, for example, build a higher specific impulse if we're building a rocket engine? Do we want to see a better mechanical efficiency in terms of the use of a fuel mixture? While exploring the physics, which is going on into very great detail here, what are the criteria for success here?
Okay. That's a good question. I'm sort of expecting someone would ask this. The question is, what's the successful criteria in terms of real propulsion systems? You see, in my, I believe it's a fourth chart, I have a statement. This perfect confluence of the long, old scientific problem, immediate needs, short-term, near-term. Because all those engines you see, the design so far is rather Edisonian. And they don't know the flame. They depend on the understanding of the flame, how fast flame propagates to burn out the fuels for the engine length, for the engine size, for how to mix. Understanding of those basic physics gives you not only and the understanding of flame, gives you what necessary database to develop the models. Also, those knowledge directly translate to the design of the engine. For example, I give you a scramjet example. Scramjet, the length of scramjet could be this long, could be this long, depends on what? Depends on two things. One is how well things mix. When things mix, how flame propagates. If the flame speed, if you can view the flame speed, is the ratio of the flame propagation angle, is the ratio of the flame speed versus divided by the velocity. And that determines angle. If you understand that flame speed, you know the angle, you know how long you can design and design the engines. So those things are immediately needed. So that's where if you say that short-term success is there. Long-term things, you understand structure, you build model, you give me far more theoretical basis for all those engines. This is so essential to that. And the immediate impact will be short-term, you will see it. Mid-term, you'll see it. Long-term, you'll see it.